Hello everyone, my name is Caleb, and in this tutorial I'm going to be discussing figure 10.13, sleep in marine mammals. Now, as you can see here, we have our little buddy dolphin. He is going for a little bit of a snooze tonight. Here he is entering stage 1 sleep. This top reading here is representing an EEG reading of the right hemisphere, and this bottom is representing an EEG reading of its left hemisphere. This may not be too important at this moment as they look very similar, but it will become important much later on. In this tutorial, we are going to compare and contrast the sleep cycles of marine mammals and see how they are different in humans or other land mammals. As you can see in this stage 1 sleep, it is characterized by desynchronization, and you can see vertex spikes here. It's a fairly low amplitude, high frequency brain state. As our dolphin moves on, it enters stage 2 sleep, much like we do. Here we encounter a little bit higher amplitudes, a little bit lower frequencies, and it's characterized by an intermediate desynchronization. However, in this state, we still see sleep spindles, much like we do in our own sleep, and we see K-complexes, just like we do in our own sleep as well. Now, where we differ is once we get to stage 3 sleep, otherwise known as slow wave sleep, or SWS. Here, the readings look much different. Here, we can see the characterized slow, very high amplitude delta waves in the right hemisphere, but we don't see them in the left hemisphere. And as we go on through time, we lose those delta waves in the right hemisphere, but we gain them in the left hemisphere. Now, this is called unilateral sleep because it utilizes only one hemisphere at a time to engage in stage 3 sleep. A reason for this could be because marine mammals, unlike other types of aquatic fish, cannot synthesize the oxygen from the water and must come up for oxygen in the air. And in order to do that, they cannot remain, as we might say, completely asleep in our own context, as we are able to utilize delta waves in both hemispheres. However, they utilize only one at a time so that they are at least partially able to move and come up for air throughout their sleep throughout the night. If you need help remembering this being called unilateral sleep, I kind of like to think of it as a unicorn, as unicorns only have one horn, whereas a unilateral sleep uses one hemisphere for sleep at a time. Now, as you may guess, there is surprisingly no REM sleep coming next after this as well. Why might this be? It's for a similar reason that they can only utilize one hemisphere for stage 3 sleep at a time. Sea mammals must come up to breathe because they cannot go without oxygen from the air. If they do not come up to breathe, they are unfortunately not going to last through the night. As they need to move their body in order to get it up to the air, that contradicts REM sleep's profound muscle relaxation that is found in mammals like us, in which when we enter REM sleep, all of our muscles are completely relaxed and are not activated in any sort of way. If all the muscles in this marine mammal weren't going to not be able to contract, then it would not be able to come up for air, and thus it is impossible for marine mammals to engage in REM sleep, unlike most other mammals that we have discovered. I hope that you enjoyed this tutorial.